So look at this configuration. I have a connected body system given by this bar AC. Bar AC. Bar AC. And here this point A is a fixed point. It's not a fixed point. It is by a hinge joint. It's not welded point. So it's a hinge point. So this AC can rotate about this point A. This is a hinge point. This is a hinge point. A fixed point in a rigid body is this point A supported by a hinge, because this point A is not going to move out, and the force, external force, if it is applied at this point, will not participate in the work. That's what we have seen in the discussion. So instead of a force, if I apply a couple here, that would create a work in this system. Right. So consider that this weighs 7 kg. The mass of this bar is 7 kg. One end is hinged, the other end, the point C, is now constrained by the spring. So I have here a spring. On the other end of the spring is constrained to roll or roller attached like this. It's a horizontal platform. It's a horizontal platform. So this point is B. Right. So the angular orientation of this now is 30 degrees. Is 30 degrees. And this is uniform bar. This is uniform bar, slender bar. So uniform slender bar AC, A is hinged and C is constrained by a spring. Spring. So what is the spring constant here is K, that has to be found out, that we do not know. There is a spring constant K here, and that constrains this motion. So the weight would be acting at this point. That is 7 kg into 9.81 Newton. So 7 into 9.81 Newton. And what is the other force? The force that is coming from here, that is Fs, spring force. Other than that, there is external couple that is also acting, right? Because this 7 kg and the spring stiffness would balance, and this orientation can be obtained. But to have this 30-degree orientation, additional to this weight of the bar and the spring force, there is also an external couple that act in clockwise direction. And that couple value is 50 Newton meter, right? So this is that couple acting in this. And what is the length of this bar? The length of this bar, L, is 2 meters. Let's consider this. So now what is the question is, what is the K value? What is the K value of the spring under equilibrium? To determine K of the spring at theta equals 30 degrees. At theta equals 30 degrees, right? Because that is important. If theta is 15 degrees, then K value is different. So this bar is acted upon by external couple and its own weight. Of course, it is constrained by the spring. Now this angle here is going to dictate this value of spring force for equilibrium. In turn, you would get your K value. So now you have to find this K value, and this can be obtained through conventional static equilibrium equation. I can draw its free body diagram and solve for it, or I can also solve by a virtual work method, because this is connected body system. So connected body is not necessarily to be connected only by rigid links. We can also include a flexible link called a spring here, like this. So now, how do you go about solving this? By virtual work method is what I'm going to explain. To solve this problem by virtual work. So how do you do that? What is principle of virtual work state? It is sum of all the work is equal to 0. Sum of all the work done, total work done in the system is 0 because of virtual displacements. So how do you give the virtual displacement? Consistent to the constraint and the direction of the forces acting. So let us consider always in such kind of connected body system a reference point which is a hinge point. So this point is 0, 0. So with respect to this, I would be able to write a coordinate of the points where the forces are acting. So this point is say this is point D, let's call. So what is the coordinate of D with respect to this? I can write if I have my point reference here. I can write the coordinate at point C. I can write the coordinate at point B. So this is collinear. It is along this x-axis. So this is my x-axis and now this is my y-axis. So this entire unit is in which quadrant is in the fourth quadrant. Like that I can describe if I give a origin and a coordinate system in the physical mechanism given or the rigid body, connected rigid body system given. So here, what is that additional statement is if the delta, this displacement in the spring is 0, it is also additionally given. When theta is 0, the displacement, deformation in the spring deformation, delta is 0, that is given. So if theta is 30 degrees, what is the deformation that one can identify? How do you identify that? The length of this is given 2 meters and this angle is 30 degrees. So what would be this length? I can find out. So the spring theta is 0. There is no deformation in the spring. Deformation in the spring. Right? So when theta is 30 degrees, what is the deformation? Is this. So when deformation is 0, what I mean by that, this bar AC is horizontal. When theta is 0, what do you mean by that? Bar AC is horizontal. So AC is horizontal. That's the meaning. That's why delta is 0. When theta is 30 degrees, now I have this entire length. What is now appearing in the configuration is the deformation in the spring. So what is the deformation at that time? Theta equal 30 degrees. That would be from this geometry, one can work out. It is 2. This is a right angle now. So this angle is 30. So this would be 2 meters sine theta. So 2 sine 30 degrees. So that's going to be 2 into 1 by 2. That's 1 meter. So this is the deflection that is there in your spring. So this is all your understanding. Then I can write my virtual work principle by this simple statement. Sum of delta U is 0 and that would be given by first there is a couple M and that's clockwise couple. So let me take clockwise couple convention negative into d theta. So this d theta is at point A. So d theta A. So how do I represent the orientation of this bar when I have this reference? Always from horizontal in the counterclockwise sense. That angle is positive. So this is that angle. So this angle, how do I represent? 360 minus this angle theta. So let's call this angle theta given 30 degrees, but let us assume this is theta. So this orientation theta A now, theta A here is 360 minus theta. I would read like that, right? So the angular displacement here is now theta A is this angle shown here. So if this couple is applied, what would be change in angular position is what is given by d theta A. So d theta A is angular displacement, right? D theta A or delta theta A, small. So let us use this letter delta. This is very small quantity. And an external force is weight. So weight is acting down, so minus. So the convention what we follow is this always mechanics. So to the right, upward force positive, counterclockwise movement positive. This is the convention that we follow. So look at that force and couple directions and follow the conventions to represent here. So since the weight is acting down, it is minus 7 into 9.81, and the expected virtual displacement for point D would be, since it is vertically acting, this point displacement in vertical direction, change in position of D in vertical direction. So that I write it as delta YD, right? Plus spring force Fs, that is why here plus I have put, it is upwards of plus into delta YC. So that's equal to 0. So this is what is total work in the system, which is under equilibrium, is equal to 0. When the system is under equilibrium, you are giving a virtual displacement. You are assuming there is an arbitrary displacement consistent to the direction of forces and the couple. And then you are working out for that expression of work and then add all of them, and that's supposed to be 0 because there is actually no displacement. That is why these displacements are called virtual displacements. So what are those virtual displacement? Delta theta A, comma, delta YD and delta YC are called virtual displacement. So how do I find these virtual displacements? These virtual displacements can be found out simply writing the position of application of these forces and couple and differentiate them. That's all. So I would be able to write the position first for a couple acting at point A. So what is its angular position is given by theta A. This is 360 minus theta. This is what is theta A, given by theta A. This is the angular position. So now what is delta theta A is what is virtual displacement. Virtual displacement. So this is position, can be linear position or angular position, and this is virtual displacement. This is virtual displacement. So delta theta A would be minus delta theta because 360 is constant. So this is virtual displacement. Similarly, now what is the position of YD? So delta YD is virtual displacement. So YD is what is the position? So YD is a linear position, Y coordinate with respect to point A. And that would be, if I consider the entire length of the bar is L, it is L by 2 sine theta, dictated by angle theta there. And this position coordinate is below negative direction, so minus L by 2 sine theta. YD is written as minus L by 2 sine theta. Is that clear? Why there is minus sign is because the reference point is here and the entire thing is in fourth quadrant. So this position is below horizontal axis. So this is negative y-axis. So this vertical position from here to here is what is given by L by 2 sine theta. So that is the position. So now its virtual displacement delta YD would be differential of this. So that is minus L by 2 cos theta into delta theta. Right? Similarly, YC would be minus L sine theta because length of the bar into sine theta is what is this. So delta YC would be minus L cos theta theta. So that is all. So now I can substitute this virtual displacement in this expression of virtual work principle equation 1, and I would be able to solve for unknown. So what is that I'll get if I substitute that? So I have here M is given by 50 Newton meters, so minus 50 into delta theta A. So delta theta A is minus delta theta and minus 7 into 9.81 into delta YD, that's minus L is 2, so 2 by 2 cos theta del theta and plus Fs. So plus Fs. Fs is given by Ks, K into delta, K into delta. So let me put that over here. K into delta into delta YC. So delta YC is L minus L cos theta del theta. This is all equal to 0. So now you see here, if you follow this, so here it is plus, right? If you follow this coordinate writing and differentiate, and the sign in a differential will automatically take care of consistency of the work. What do you mean by consistency of the work? If the work done by a force, the force and the displacement in the same direction, that's called positive work. If that is opposite, then it is negative work. So you can see that here that is obtained through this automatically. So you can see that this has become now 50 delta theta, and this goes and plus 7 into 9.81 cos theta delta theta, and here it is this minus. So minus 2 L is 2 into K into delta. We have just got that's 1 meter. So 1 cos theta delta theta, that's equal to 0. So here it's minus quantity and these two are positive quantity, right? So otherwise these two would be negative and this is positive quantity. So that can be clear here from this that consistency is maintained. So if I assume that this is Fs is going to do a positive work, this goes up. So force into this delta K, the spring force into delta would be positive. These two are negative work because weight is acting down. So this point is going to go, that should be negative. And the external couple acting here expected to rotate in clockwise sense, but Fs makes this angle to decrease. So again, it's negative. So the consistency takes place. Or if you assume that this moment make this go further, so this would be positive and this would be positive and this would be negative. So that consistency would automatically taken care if you follow the convention to represent the forces, external forces and external moments, and write the coordinate and differentiate, you get a virtual displacement with an appropriate signs that would ensure automatically. So this is that I recommend. You first write the principle, then write the coordinate, differentiate, get the virtual displacement, substitute and solve. So in this delta theta is common, that is cannot be 0. That's what is the requirement of virtual Earth method. So the remaining quantity 50 plus 7 into 9.81 cos theta minus 2k cos theta can be 0. So delta theta cannot be 0. So this is 0. So I can solve for k. Therefore, k would be 50 plus 7 into 9.81 cos theta divided by 2 cos theta. So if I substitute theta equals 30 degrees for the given orientation in the problem, I would get here this k value as 63.2 Newton per meter. That's all. So this is how one can solve this problem, right? And this method followed is called a virtual Earth method. Let us solve one more problem. Again, let's consider this problem what we have done during our frame analysis. So let me consider a frame made of two links rigidly